Next, let's look at this example, which is going to be problem number 108 from the end of chapter 10 in your textbook. This is a mostly conceptual problem, although it involves some quantitative reasoning, I guess. So we're told that there are two 112-liter tanks filled with gas at 330 Kelvin. So they both have the same volume and the same temperature. One contains 5 moles of krypton, the other contains 5 moles of oxygen. So they contain the same number of moles of gas particles as well. Considering the assumptions of kinetic molecular theory, in other words, sort of the behavior of ideal gases, rank the gases from low to high for each of the following properties. So we have collision frequency, density, average speed, and then pressure. So using what we just talked about, try to think about conceptually how you would compare the two on those 4 bases. So try that on your own and pause the video, and when you come back I will walk you through what the answers should be to this. Alright, hopefully you tried this on your own. We have one container with krypton and another container with oxygen gas. And both of these containers have the same volume at the same temperature, and they both contain the same number of moles of gas. The only thing that's different about the two is one of those is krypton, and the other one is oxygen. And specifically, if we write down those molar masses, because that'll become important later, for krypton, if you look that up on the periodic table, that's going to be 83.79 grams per mole. And for oxygen, each oxygen molecule has 2 oxygen atoms in it, so 2 times the atomic mass for oxygen gives us 32.00 grams per mole. So what this tells us, besides what their molar masses are, is we can scale those down to the molecular level and say that a atom of krypton, since it doesn't exist as molecules, just individual atoms, is going to weigh significantly more than a molecule of oxygen. And that's going to have some significance in interpreting what the answers are here. So in terms of collision frequency, in other words, how often are the particles running into each other? Now, collision frequency on its own depends on a lot of things, but most of those things are constant here. So the volume and the temperature and the number of moles of gas particles, for instance, are all the same. And really we have the same density of gas particles in terms of how many gas particles there are per unit of volume, so moles per liter, in other words. So the collision frequency, how often those particles will run into each other, the only thing that's different between the two containers is going to be the speed of the gas particles. So the faster they're moving around, the more often they'll run into each other, which I think that makes sense. Now, if these two gases have the same temperature, then that means each particle has the same average kinetic energy in both the krypton and the oxygen tanks. So if they have the same amount of kinetic energy, but one consists of much heavier particles, the one with the lighter particles, those particles on average are going to be moving around a lot faster than the heavier particles in the krypton. So the oxygen is going to be moving around with a higher average speed per particle than the krypton will. So if we're ranking these from low to high, our krypton is going to have a lower collision frequency than our oxygen will. So oxygen will have a greater collision frequency here. So that's A. For B, we have density in grams per liter. Now, we just said that the molar density of both gases is equivalent, so the same number of gas particles for any given unit of volume. However, we've also previously stated that the gas particles in krypton weigh quite a bit more than they do in oxygen. So the oxygen gas will be less dense than the krypton gas will. And so ranking those from low to high, krypton will have a higher density than oxygen gas. And if you wanted to answer a lot of these problems, certainly density or average speed or pressure for B, C, or D, you could actually plug in numbers to figure out what the exact values are. But as you can see, when all we're doing is comparing them, we don't need to do any complicated math. We can just kind of reason through things with what we know about kinetic molecular theory. To answer part C, I think is going to be pretty simple, since we already invoked average speed in discussing the collision frequency. So, as stated previously, with two gases at the same temperature, and they are both at 330 Kelvin, the average speed of the gas particles is going to be inversely correlated to the molar mass, because all the gas particles on average should have the same kinetic energy in both the krypton and the oxygen. And since the krypton particles are a lot heavier, they're going to have a lower speed for the same amount of kinetic energy. So in oxygen, the average speed of the gas particles will be considerably higher than it will be in krypton. And then finally, pressure. Now, to go through pressure, I'll just remind you of what the ideal gas equation is. That is P times V equals N times R times T. And specifically, if we want to rearrange this to solve for pressure, we can do that. So that's going to be N times R times T divided by the volume. And what's interesting about this equation is if we are looking at pressure, that depends on the number of moles, N. That's constant between both gases. R is always a constant. It's always 0.08206 liters atmospheres per mole Kelvin. The temperature is the same in both cases. It's 330 Kelvin for both gases. And so is the volume. Both gases exist in 112 liter tanks. So for both gases, if we wanted to solve for the pressure, which we don't need to do explicitly, we'd be plugging in the same four numbers in the exact same ways into the same equation. And so in terms of pressure, actually, neither one has a higher pressure. The pressures are equal. So the pressure in the krypton tank is going to be the same as the pressure in the oxygen tank. Notice that for pressure, it doesn't explicitly depend on the molar mass of the gas, so those two will just be equal under the same conditions.